Hello, everyone. I'm Raluca. I'm a faculty of computer science specializing in security at UC Berkeley, where I work in the area of privacy preserving computation and secure computation. I'm also co-founder and president of Opaque system, which commercializes technology for privacy preserving computation. Today, I'm going to tell you about the open source we've been developing in my group at UC Berkeley called MC Squared, which enables learning on confidential data that no one can see. Let me give you the abstract problem it's trying to solve, although this problem shows up in many instances. Organizations often wish to learn from data from multiple organizations, but they cannot share it because it's confidential or because there are privacy regulations and whatnot. Here's one specific example from money laundering. Criminals often hide their traces by doing money laundering across different banks. And the banks would like to detect this money laundering because they're losing a lot of money every year to money laundering. But because the criminals are hiding their traces across the different banks, any one bank alone has a really hard time detecting these criminals by looking only at its data. This is why the banks would really like to put all this data together and start identifying the loops, transactions that these criminals make. It becomes much, much easier to detect them that way. However, the problem is that the banks are in competition, so they can't share data with each other, or there are privacy regulations and issues like that, which basically prevents them from putting their data together and finding these criminals. Now, this quote from the Chief Risk Officer of Scotiabank, and we're collaborating with Scotiabank on this use case, says that if they were able to put together their data and jointly perform money laundering, they would detect such attacks, such criminals, by orders of magnitude more efficiently. So they really need the technology like that. Besides this, the need to collaborate with confidential data that people cannot see shows up in many other cases, in many other financial cases, such as fraud and human trafficking detection through financial forensics, or flu prediction or cancer diagnosis, and so many other cases. This is why my students and I at UC Berkeley have been developing the MC Squared platform, which stands for Multi-Party Confidential Computing. So MC Squared enables organizations to learn on confidential data from different organizations without showing it to each other. And this is open source that you can play with. And basically, the technology embodies the principle of sharing without showing the data. So you can use MC Squared either in the cloud just for your own data to protect the data from the cloud or from hackers, or you can use it to collaborate across your different divisions or branches that can share data with each other, or you can use it to collaborate with a whole other organization whenever you need to learn from data that some parties cannot see. So how does MC Squared actually work? And I won't go into a lot of technical detail, but I'll just give you a very, very high-level overview. Currently, in doing this kind of privacy-preserving computation, there are two main state-of-the-art technologies. One is purely cryptographic, such as you might have heard of secure multi-party computation or homomorphic encryption, and the other leverages recent hardware advances like hardware enclaves. And my students and I have done a lot of research over the past bunch of years on each one of these technologies because they have a trade-off. The cryptographic approach is cleaner from a mathematical standpoint and it doesn't need specialized hardware, but it's very slow still. You can use it for simple computations like averages or counts, but you can't yet use it for the kind of realistic machine learning training people do today or rich SQL analytics. Hardware enclaves, on the other hand, are much, much more efficient. So in the rest of this talk, I'm going to focus on hardware enclaves and the technology that we built using them. So let me tell you what hardware enclaves are at a high level. They're basically isolated execution environments that is enforced by the hardware. So they protect against an attacker that has root access on a machine or compromised operating system, because that attacker is only going to see encrypted data. Basically, deep down in the processor, under the die, there is an engine called ME, which is a memory encryption engine. So it encrypts all the data going out of the processor into main memory. So if an attacker has access to the operating system or has administrative privilege, the attacker can try to peek into memory, but it's encrypted. Now, whenever the data comes back into the processor, this ME can decrypt it so that the core can compute on the regular data, unencrypted data. And this is why it's very, very fast. Okay, so it's fast because you can compute on regular data inside the processor, but it also provides strong security because to any software on the machine, main memory is encrypted. The nice thing about hardware enclaves is that these days they are available on public cloud. So this is a very timely technology. For example, Azure has Azure Confidential Computing, in which they provide a public cloud with this kind of hardware enclaves. Hardware enclaves do have a downside, and that is the side channels, which are indirect ways of information leaking. However, there's a lot of research into how to protect against those, and a lot of my research and my students' research is dedicated to protecting against those side channels. So a lot of MC² is incorporated in those mechanisms and protects against a very large class of side channels. So let me give you an example of how one can perform machine learning on confidential data using MC². And let's say we have a bank here from the anti-money laundering example. Now, the bank is going to run the MC² client, the client software. And the bank also has, as part of this client, is going to generate a key with which its data will be encrypted. Now, on the cloud side, we have a deployment of MC² with enclaves. So now the first thing that the bank does is going to have to check that these enclaves are being set up correctly. And this procedure is called remote attestation, and it's a very nice property of hardware enclaves. It enables a remote party like the bank in this case to verify what's running on the enclaves in the cloud. So the bank can actually check that the desired software is running on those enclaves. For example, the desired anti-money laundering learning software, but nothing else. There's nothing else. There's no malware or nothing else, right? There's exactly the software that the bank intends to run. That's what's going to run on the enclave on the bank's data and nothing else. So now after this remote attestation procedure happened, which involves actually hardware mechanisms on the enclave side, but after this remote attestation procedure verified, the bank can exchange its key with the enclaves over a secure channel. So now the enclave, if it receives data encrypted from the bank, it can decrypt it and compute on it. All right. So now our bank is going to take some data, encrypt it, maybe store it in the cloud encrypted or load it encrypted from the cloud. But the point is that it's going to be loaded into the enclaves, and the enclaves can decrypt this data because they have the key of the bank. Now the enclaves can compute on this data some training script, let's say, provided by the bank. Okay, and they're going to compute on the data deep inside the processor is decrypted, but to any outside party, to any software attacker, it looks encrypted. And then they're going to produce the results. The results are going to come out of the enclave encrypted because everything comes out of the enclave encrypted. And then the results are being sent to the bank, and the bank can decrypt them and enjoy them. So now, what happens if we have multiple banks that want to collaborate with each other? It's very similar. The banks each are going to have their own key. They each are going to verify the deployment of enclaves in the cloud, send their encrypted data with their encrypted key, so the enclaves can compute on the data from all the banks and compute some aggregate results, for example, suspicious anti-money launderers. And then these results are encrypted under everyone's keys and returned to the banks who can enjoy the results. All right, so I'm going to show you a demo of how MC² works on the example of anti-money laundering, and I'm going to take it step by step from the command line so you can really see what's happening inside the system. But of course, if one uses MC², it doesn't show to the client all these details, right? It's easy to use. It's much more abstracted out. But here I want to show you step by step what's happening so that you can really, get a deeper understanding of the system. All right, so in this demo, we're going to have the MC² client installed on the premise of a bank. Also, we're going to have a deployment of MC² on Azure cluster, in this case, Azure Confidential Computing. On the top screen, you're going to see the inner workings of the client machine and the output and what it does on the client side. And on the bottom screens, you're going to see the inner workings of the cloud side. So the virtual machines with hardware enclaves belonging to MC² in the cloud. Now, again, this is going to be command line, but all of these details will be abstracted out in 3 simple steps in the actual open source. Okay, so first the client is going to encrypt the data and upload it. Then the client is going to attest that MC² is deployed properly on the server side. After that, the server, the cloud, is going to train the model, and then the client is going to download the results and decrypt them. Okay, so now we begin the demo. So on the client side, we have some data. This is some synthetic data we obtained from Scotiabank. Let's take a look at it. We're going to use this data for training. So it has a customer ID on every row and some synthetic transactions that this customer made. And so we're going to use this data to train a money laundering model. And then we're going to use it to perform predictions for money launderers. So we have also testing data that looks very similar. Okay, so now on the client side, we're going to encrypt the training data and testing data. And we're going to upload both of those to the cloud. So let's take a look. This is the encrypted data. It looks like gibberish. It's random, it's encrypted. Now we're going to transfer this to the cloud, both the training data and the testing data. So let's try to visualize the data on the cloud and see how it looks like. And it's encrypted, right? Because the server, the cloud, is only going to see encrypted data. All right. So now, back on the client, we're going to have to prepare the training script. Well, for that, we're going to start with just a regular data science training script, let's say in this case for decision trees. And this is just a regular script a data scientist would write with no expertise of MC² or confidential computing whatsoever. Then, to make this run in a privacy-preserving way with MC², one just adds basically MC² and initializes it. Just a few lines of change, that's it, but no actual change to the actual training script. So it's very easy to use. All right, now we're going to start the cluster on the server side. You're going to see some output on the first VM. You'll see what the VM is doing. And on the other VMs, I'm not going to have any output, but using the htop command, we can see when they are utilized. All right, so back on the client, the first thing we're going to do is we have to deploy this script on the VMs in the cloud, but first we're going to run the remote attestation procedure to check the environment at the enclaves. The check proceeded successfully, so as a result, the servers, the cloud, are starting to train. They're loading encrypted data, they're encrypting it deep inside the enclaves, processing, and you can see that the VMs are utilized. So outcomes in the cloud, the trained model and predictions, we can try to visualize them. So we can see that the prediction results are also encrypted, because always on the cloud, everything will be encrypted. The attacker of a cloud cannot see the data, it's all encrypted. But on the client side, we can download these results and we can decrypt them. So here we can actually view which customers are believed to be launderers and with what probability they are believed to perform money laundering. Okay, so hopefully this demo gave you a sense of step-by-step of how MC squared works. We wanted to take the MC squared open source further from, instead of just being an open source artifact that's based on research artifact, to make it into something that's easy to use, something that one can rely on, something that has full-time support and is efficient. So that's why some of my students and I and colleagues, we started a company called Opaque, which does exactly this. Packages MC squared into a very easy to use, robust, very functional and efficient system. This is the team behind Opaque. It's 3 of my students, 2 of them graduated with PhD and 1 with master's, experts in this area, and my colleague Jon Stojka. So as part of Opaque, we provide 3 modules: machine learning in a confidential way, federated learning in a confidential way, and analytics in a confidential way. And these are running on top of major cloud providers like Azure. The nice thing is that we've already had a bunch of adoption, either in production already or internally at a number of companies. All right, so in conclusion, Opaque enables machine learning on encrypted data using our open source technology MC squared that we developed in research over multiple years. It's open source, you can freely play with it, give us feedback, let us know if you have any use cases, if you would like to collaborate, or if you'd like to use the system for any of these, please go ahead and contact us and we would be happy to work with you on helping you adopt MC squared. Thank you.
Look, it was very interesting. As I said before, this is an area that we are also experimenting with, even though not on an enclave solution, but on we're working with full homomorphic encryption. But I'll be sure to be in touch with you because it sounds very interesting. One question I have for you is, what do you think the greatest challenge is in making this a commodity, something available, working for everyone?
The biggest challenge is regulations, right? So a lot of companies have confidential data they cannot share, and they would benefit from doing this kind of privacy preserving computation learning. But regulation is a big hurdle because companies across different countries or in markets like financial or medical, they have to comply with very strict regulations. So we need to make the regulatory bodies understand enclaves in cryptography, right? And enable these kind of technologies to be compliant. So that's, I would say, a slow process, and it's one of the biggest challenges in my opinion.
Thank you very much.